Okay, before I even start this problem, I just want to mention that these Taylor polynomial problems, they all look pretty intimidating at the beginning. And every single student that I've ever had went from being pretty hopeless on these at the beginning to not knowing where to start to being a lot better of them at the end of our review here. Okay, so just try to be patient with that. I know it kind of sucks when you're worried about that stuff there, but let's just take it one problem at a time. And what I want you to do for the next few minutes is maybe just sit there and listen and pay attention for the next few minutes, and then try it on your own from scratch and see what you can do from scratch. And then you can go back and look at the video again if you get stuck at all. But once we get like, 5 or 6 of these under our belt, then I think what it would be is a good idea to actually group those 5 or 6 problems together and study those like back to back to back to back. I mean, that's what helped me kind of get a grasp of some of these problems. And then some of these earlier ones, the algebra just gets messier. They're not as neat as like the last 7 years worth of testing were anyways. So I just like to get some of these beginning ones out of the way to kind of, smack you in the face a little bit and then just kind of get that really uncomfortable feeling. And and it will get better. I just want to say that's what I'm missing the most about not being in the classroom now, is letting you know that, hey, whatever feelings you got about this stuff, whatever stresses and worries you got about this stuff, every student before you has had those same worries. And so it always gets better, right? And we don't get 90-some% pass rate on this test for no reason there. We work our butts off and we're going to kind of get a grasp of this stuff there. So, all right, let me just get into the problem. One problem at a time, and we'll get better at these things, okay? You'll start to see some similarities and some things that you should try when the time comes. So typically on a Taylor polynomial, sometimes they will give us a whole string of things already. And then typically I'll see like a derivative notation there or integral notation there, and I'll go ahead and I'll take a derivative and I'll do an integral. And then when we have to create a Taylor polynomial all by ourselves, that's when I typically will either start with one of two things. I'm going to start with our main definition from your Taylor polynomial videos, or you're going to start with that purple sheet and you're going to have something memorized, like the ln of x1 or the cosine of x1, and we'll start with one memorized from that purple sheet. This one here, when I see this 6-degree Taylor polynomial, I don't see any ln's or sines or cosines or anything that I'm going to start with that memorized purple sheet. We'll see a problem like that in the future. I'm going to start with my main definition of a Taylor polynomial straight from your BC extra video lectures that you took notes on, right? So I have a 6-degree Taylor polynomial, and that's going to be, and it says about x equals 2. So there's our c. So that's what I'm going to go f of 2 and an f prime of 2x minus 2 over 1 factorial, of double prime of 2x minus 2 squared over 2 factorial, f triple prime of 2x minus 2 cubed over 3 factorial, all the way down to that 6th power and that 6 factorial, right? So that's just straight from your videos. Start with that. It's either going to be that or it's going to be something from that memorized purple sheet, okay? So I always write that down. That helps me. So there's my 6-degree Taylor polynomial. And then what it's telling us up here in some of this confusing looking language, it's mentioning when we have an odd derivative, right? So when n is odd, the derivative will be 0. So that means the first derivative, third derivative, fifth derivative, all of those derivatives at 2 are going to be equal to 0. So that's just 0 times something, 0 times something, 0 times something. So all of those, I just cross those out. Those are all going to go away. And then when it says when n is even, so the second derivative, fourth derivative, sixth derivative, we're going to be using this to evaluate those derivatives, okay? So an even derivative I got written down here is that little formula they gave us. So when I'm doing the second derivative, I plugged in 2 for the n. So that gave me the 1 factorial over the 3 squared, and then this 2 factorial was already there. And then when I did the fourth derivative, I plugged in the 4 for the n. So I gave 4 minus 1, I got the 3 factorial, and I got the 3 to the 4th, and then that 4th factorial was already there. And then plug in the 6 for the n, and you're going to get this thing stuff here. And then the x minus 2 squared to the 4th to the 6th, that just carries down. And then they told us that the f of 2 was equal to 7 in the original problem up here. All right, so that's all of the stuff we need for that first part. So creating a Taylor polynomial, again, it's just going to be from your videos using your main definition, or it's going to be, you know, from that purple sheet that will have a few things memorized right there. And so we're going to see all of the stuff that I possibly have ever seen on these things when the time is right. All right, just do one problem at a time and try to wrap our brains around that. It will keep getting better and better. All right, so part A, we'll get good at stuff like that. Now part B, we were supposed to look at the patterns and try to come up with some of the patterns. And sometimes my brain works really well with that and I can see those really well. And then sometimes I struggle with that here. And then that stuff has gotten like better the last so many years worth of testing where they don't have us do much of that, or the even and odd stuff, we can kind of at least kind of have something to go off of there, right? But when it says what is the coefficient of that x minus 2 squared, 4, or 6, so notice that you got the x minus 2 squared, the x minus 2 to the 4th, the x minus 2 to the 6th. So that's your x minus 2 to the 2n. What they're asking for is the stuff in front of that, right? And so what I did, I put these little boot-shaped things in the coefficients. That's what we want to try to get a pattern for and get like a little formula for. So usually when they have us do a pattern, a lot of times it ends up being the even and the odd stuff, right? So even, you represent that as like 2n. So like 2 times 1 is 2, 2 times 2 is 4, right? So 2n will represent an even number. And then an odd number would be 2n plus 1 or 2n minus 1, depending on the situation. So what I did to come up with this, as I saw 3 squared, 3 to the 4, 3 to the 6. So when you see the even powers right there, right away I said that was 3 to the 2, and that was the first thing I wrote down, was that 3 to the 2n. And then I noticed that this is a 2, this is a 2 factorial, this is a 4, this is a 4 factorial, this is a 6, this is a 6 factorial. So if I put a 2n right there, those factorial numbers were the same as those exponents there. So if that was a 2n for my exponent, because it was an even exponent, I used a 2n factorial for the even, so that will give us, you know, the 2 factorial, 4 factorial, 6 factorial. So if you see the even numbers, that's going to be represented by the 2n, and then you got your factorial right there. And then when we notice on the top part, you got 1 factorial, 3 factorial, 5 factorial. Those are odd numbers. And so usually with the odd stuff, I'm either going to have a 2n plus 1 or a 2n minus 1. And then I noticed that those numbers were 1 less than, see how 1 is 1 smaller than the 2, the 3 is 1 smaller than the 4, the 5 is 1 smaller than the 6. That's what told me they used the 2n minus 1 for the odd number instead of the 2n plus 1. And then I got the factorial right there. And then like we did in chapter 9, you can rewrite this as 2n times 2n minus 1 factorial. So those will cancel out entirely, and it just simplifies to this. So that's what they wanted for the part B, is to come up with that coefficient. Now when we get to part C, part C says find an integral convergence. Now when I see that, this is going to be very similar to the videos of your BCX, your video lecture. You have a whole video over the power series and finding an integral of convergence. And that's what we're going to do right here. Although the algebra gets a little messy at the end of this problem that they typically don't have us do on the newer exams. But so here's what we got so far. So my polynomial going from part A to part C, I got the 7. And then this is the coefficient. So that just, I inserted that at the beginning there. And that's the stuff in front of that x minus 2 to the 2n that we found right here. So this is our power series. And we're going to do exactly like what we did on the video. So let me just kind of slide up a bunch of this stuff. But this is going to be exactly what we did on those extra BC video lectures right there. So watch that again if you need to. But we're going to do the ratio test. And so we're going to do limits n approaches to infinity. You're going to replace all of those n's with an n plus 1. There's your a sub n plus 1. We're going to divide it by the original, which means you're going to multiply it by the reciprocal. And for this to converge, we're forcing this thing to converge. The ratio test converges where that is less than 1. And you need the absolute value bars on these ones. And then I think you know how to do that stuff, like from your 9.6 ratio test days. We know how to rewrite this as 3 to the 2n times 3 to the 2nd, and then the 3 to the 2n's will cancel out, just a 3 to the 2nd carried out. I can rewrite this as x minus 2 to the 2n, x minus 2 to the 2nd, and the x minus 2 to the 2n's will cancel out, and I'll just carry that down. So if you want to write that down for yourself, you know, go ahead and do so. And then the other stuff we're just carrying down. And then remember, what we'll do right here is any of the stuff with an n attached to it, I have to leave on the inside of that. the x's and the numbers I'm allowed to pull out in front. And remember, we also said it doesn't matter what you do with that 9. So I'm just gonna just have Justin put the ends right here. It doesn't matter what I do with the 9, but I'm just gonna pull it out just to get it out of there. And then when you pull it out, the absolute value bars are still there. And then you have the limit of the rest of the stuff is less than 1. We can do our leading coefficients here. And we all know that's equal to 1. So you have this thing times 1 is less than 1. And then remember, that's the less than sandwich, right? When you have the absolute value is less than something, we sandwich that thing in between the -1 and the positive 1. So let me slide that up to see the whole rest of the problem here, and then we'll talk through it. Okay, I multiplied everything by the 9 to get this. Now this was a little bit weird. I don't remember seeing this thing, and usually it's just a nice interval and you just add like 5 to all 3 parts and then we're done with that. But this is a little goofy. They got a little crazier with the algebra back, on those earlier exams here. Now, what I recognized right here, I had a nonlinear inequality, so that was going to represent like the number line thing that we reviewed in our summer packet. Since this expression was being squared, I knew it was already bigger than that -9. So I just really just ignored all that, because -9 is always less than something squared, because that means that's going to be like 0 or positive, right? So -9 is always going to be smaller than that. So I didn't have to worry about that at all. That's why I just focused on the rest of the problem. Now, when you have the nonlinear inequality, it doesn't help us to square root both sides and do a plus or minus or anything like that. You have to get everything on one side, get 0 on the right, and then factor that, find the zeros of that thing, put the zeros on your number line, and then you choose a test point to see which one works. So I put the zeros on my number line. There's no bar right there, so they're open circles, and then I use 0 for the test point. So I plugged in 0 minus 5 as a negative number, 0 plus 1 is a positive number, and then the negative times a positive gives us a negative. And if you don't see any even exponents right there, the signs will alternate. And you're trying to pick out the interval where it's less than 0. That's the negative interval. That's in between the -1 and the 5. Now, if you need to brush up on that power series interval convergence video, go ahead and do so. Now, the rest of this problem here, anytime you do your ratio test and you get an interval like that with 2 different numbers, you need to check the endpoints, because remember, at the endpoints, when the ratio test, when this is less than 1, that's when the ratio test converges, right? But remember, when the ratio test is equal to 1, that means that thing is inconclusive, which means you don't know what it does at those endpoints there, whether it converges or diverges. So we need to check those separately. But if you get an answer like x equals 2, or if you get an answer from -infinity to positive infinity, you don't have to worry about doing the endpoints right there. So let's just kind of pay attention to the rest of this for the endpoint checks there. And this is something I typically will get questions on even like a couple of weeks before the actual test. But like, oh, I got a handle of these ratio test problems and these Taylor polynomial problems, but I'm really bad at checking the endpoints. Could we go through one of those? And so, that's the benefit of having some of these videos, is I'll explain how to check the endpoints anytime we need to, and we can watch those as many times as we want there. But students usually tell me after we go through it, like, oh, that's actually pretty easy. So just kind of believe that you're just plugging in something here. Your goal here is to turn this into an easier chapter 9 problem, turn into a P series, turn into an alternating series, or, a geometric, or just anything that's just going to be easy, what we already know how to do. So what we're checking for, these are the X's, right? So we're going back to this thing that we got right here. And I'm going to plug in x equals 5 there. And I'm going to plug in x equals -1. So when I plug in the x equals 5, see, I'll get 3 minus 2 to the 2n. Everything else will carry down. And so I'll just get the 3 to the 2n there. Those will cancel out. The 2, technically, you could pull out the 1/2. That's just p equals 1. That's a divergent p series, which means at the 5, I'll leave that a parentheses instead of making that a bracket. And then when I plugged in the x equals -1, up there in my power series, -1 minus 2 gave me a -1 to the 2n, and then other stuff kind of carries down. And so, I'm sorry, -1 minus 2 gave me -3 to the 2n, and then the other stuff carries down. So that's why we're looking at this guy right here. And I think I mentioned in those the extra BC extra video lectures, is that when you see something like that, you can rewrite it like this. You could pull that negative out as long as you kind of keep the exponents the same there. And then the power of that is I could cancel out the 3 to the 2 ends. And then because a lot of times when I see this left over, that's an alternating series. And I'll do like the basic alternating series test in my head or something, try and see whether that converges or not. But when it's a 2 end, that means it's always an even power. And so a negative number 2 and even power is always positive. So if it's always positive, you can just rewrite it like this, which is another P equals 1 divergent P series, which means since both of the endpoints diverge, that means we're going to leave them both as parentheses. So this is my final interval of convergence. A lot of times what will happen is like, you know, we got to check them because sometimes one might converge, one might diverge, and one will be a bracket, one will be a parentheses. Sometimes they'll both converge. We just don't know. We just got to plug them in for the X and then check it and turn to some of the easier stuff there. So you'll get better at those. You'll see some more of those where, you know, you realize that checking the endpoints isn't really all that bad. And there's our interval of convergence right there. Strawberry.